think it's not loud enough against the noise right now, but okay. Let's start on a light note. How many of you get the reference? Metal Gear Solid? Okay. Anyway, the seed for this talk has been planted 2 years ago when, after wrapping up PyCon US, I took advantage of being on the west coast of America and took the classic road trip like everyone does when they're there, like from San Francisco down to LA, up to Las Vegas, back to San Francisco, and then down to Hawaii. And this tour plus PyCon took me like 5 weeks. This is kind of where the name is coming from. And that meant 5 weeks absence from work. And with every new photo I was posting, people kept asking me whether I still have a job and how I do it. Now, it turns out I do still have a job. And it worked out so well that I took it a step further last year when I went to Africa for almost 2 months. And from those 2 months, I spent 2 weeks completely off the grid. I was camping next to elephants, which I can very much recommend. It's much more fun than going to hotels or lodges. And yeah, so basically camping in the wilderness without any internet whatsoever. And when I came back, I spent 1 month in a very small suburb of Cape Town with very shitty internet. And the water looks nicer than it is. It was 7 degrees, which is like 20 degrees more than outside here, so I guess it's hot. And I still had my job. Now, why am I telling you all of that? So first of all, when I invite people over for holiday pictures, nobody comes. So it's up to you now. And I want to express something. I'm not a lazy person. I'm working just as hard as all of you, probably. But I've managed to become dispensable for the day-to-day routine of my work. And this is what enables me to do stuff like that, or to just go to Minsk in the middle of the week. And it turns out again that attaining that status is interesting to people. So I've been asked to collect my thoughts, and I've collected a bunch of principles that I think are important for me to be able to live this kind of life. And it's going to range from DevOps to normal, like software engineering principles. So I hope there's something in there for everyone. And by the end of the talk, there will be a link with all concepts I'm talking about, all projects, so you do not have to write them down. Now let's get going. And every big change, like literally every change starts with a change of attitude. And in this case, it means that you have to start to value quality. And that, again, means that you will spend a non-significant time working on non-features. And this goes back to incentives, because everything is top priority nowadays. And if you ask your manager whether quality is a priority, they are going to say, of course, yes. No manager ever said, please do some shitty work. But the question is, how are you incentivized to do that? Because if you do not have enough time to write proper tests, if you do not have enough time to instrument your systems, build a monitoring system, build metrics, that's kind of like a construction company that says that safety is #1 priority, but everyone has to buy their own hard hats. And the fact is that reliable systems take time. And if your only performance metric is shipping new features one after another, there's a conflict of interest. But not all is lost, because there is a solid business case for reliable systems. There is a way to explain to your boss why it is important to build them, or why to spend your time on that, except apart from your vacation. And it goes down to the distinction between important work and urgent work. So if you spend most of your time with urgent tasks because the database server is on fire, or because some microservice is losing its shit, then you do not get to do important work. You do not get to build new features. And there is a graph which people just made up, but at some point, when you have so much urgent work to do, you do not get to do important work at all. So you're basically just firefighting all day, and you have no time whatsoever to create new business value. So it's better to not ever get there. So the problem is it takes some kind of long-term thinking, and that's not too common in our line of work. But maybe you can try to convince your manager now. Now, For my first point, I'm going to defer to authority, and in this case, Tony Hoare, who gave us Quicksort and is quite accomplished in all things distributed systems and concurrent systems, and he said that the price of reliability is the pursuit of the utmost simplicity. Now, if you prefer a Dutch sage, which on a Python conference is plausible, Dijkstra basically said the same. Now, a good way to approach simplicity is from the other side. So, what is complexity? And complexity is basically the number of concepts you have to keep in your mind when you are trying to reason about the behavior of a system or about the impact of changes on the behavior of your system. And humans are naturally limited in how many things you can juggle, like physically and mentally. I think the number is around 7. And once you exceed this number, you start dropping balls. And when you start dropping concepts and try and reason about complexity, it means that things happen, accidents happen. And there's even a name for those accidents. They're called normal accidents. And this term has been coined by Charles Perrow in the wake of the 3 Mile Island incident, which was a nuclear accident in the United States. And they're called normal because they are inevitable in extremely complex, tightly coupled systems. So they just happen. Now, to make it a graphic thing, so if your program is such a contraption, and I'm sure everyone in this room has a program like this somewhere doing something very important, at least I do. So it's completely impossible to reason what happens if you play with this knob. Because there are too many parts connected, and too many parts are connected to that part. What happens if that knob breaks? You don't know. You cannot tell. Although you can tell, probably the whole thing is just gonna come down, crumbling. And maybe the knob isn't even important to a very different feature, but the features goes down too because it's coupled to this little knob. And the irony here is that if you try to make this safer, more reliable, you add more complexity. And adding more complexity will again make it more likely to fail. So in the end, you have to rewrite it or try to find a way to split it up. Now, we have to differ between 2 different types of complexity. First, there's essential complexity, which is the problem you're trying to solve, the thing people are paying you to do. So like detecting cats in videos or predicting something data science. That's essential complexity. But there's also accidental complexity. And accidental complexity is something you do to yourself, which is not part of the original problem, but you have to solve it anyway. So that comes from, for example, wrong abstractions, cumbersome deployment procedures, or using ancient and inadequate tools like Python 2, for example. Yeah, I found some Python 2 code in Zimbabwe. So the question is, you have to ask yourself, how much time do you spend on accidental problems? Because you cannot exterminate them completely. There are always a certain amount of accidental complexity you have to solve. But we must not lose focus on the problem you're actually being paid to solve. So, now, what is simple software? And that's a talk by itself. It's more likely a conference by itself. But I like the ravioli metaphor, which, by the way, is used both as a pattern and as an anti-pattern. So I'm just going to use the positive one because I really like ravioli. So we've established that normal accidents happen in tightly coupled and complex systems. Now, so it follows that you should prefer to have simple objects that are self-contained and have simple relationships, which is kind of ravioli. They are small. If you do not overcook them, they are self-contained. And if you overcook them, Italians get very upset. And they have a very simple relationship. They have a surface, and the surface work against each other. No ravioli knows what's inside of under the ravioli. So in other words, they do as little as possible, and they know as little as possible about each other. Now, this gives them, again, a clear interface. And those few assumptions give you very simple relationships. You can reason about how those objects interact because they do not reach into each other private attributes, for example. And especially, you should not have bidirectional dependency, so like 2 objects knowing about each other. And I found it helpful to think of an object graph like a family tree, because if you have loops, you are in trouble. And all of this makes your objects really easy to test, because you don't need to spin up a whole network of objects just to test some little method on the side. Now, the bad design, of course, are big classes, also called God objects, because they know too much and they do too much. And they are super hard to test because of the many dependencies you need to them. You spend more time mocking than testing, and that's kind of when you know that you're doing something wrong. The problem with God classes is that they are pretty common in Python, because writing classes in Python is kind of obnoxious. You have so many protocol methods to implement to write well-behaved classes. And this is why I wrote attrs. How many of you have heard of attrs? Okay, it's not that many. So, attrs will write class boilerplate for you. You tell it your attributes, or attrs, and it will write your dunder init, dunder wrapper on all those things that are usually about the same, but not quite. Now, those of you who have not heard of attrs are probably sitting restless in their seats, dying to tell me about name tuples. And I have a passionate tirade ready to explain you why name tuples are really bad for as a class replacement. But I have very little time here, so I'm going to spare it you. But just let me say that name tuples are great if you need a tuple with names. It's like right there in the name. But for classes, it's not a good solution for many reasons. And that's why I wrote attrs. And it will give you a simple class. It's mutable. There are no weird methods on it which you cannot remove. You do not have to subclass dunder new if you want to influence initialization. It has validators, it has converters, and default values, including factories. So you can finally have your default empty list without making the most basic Python mistake that everyone makes when starting out. Now, let's move on to operational complexity. And this ties nicely in with what Tarek talked about, actually. And it's the complexity of running your infrastructure and all your systems. And I don't think that it's controversial to say that distributed systems are hard. And let's look at a very simple one. I think this is fairly standard. You have a client which talks to a CDN, which probably is not in your part of your infrastructure or part of your data center. And it talks to your application, and your application talks to a work queue like Celery, which Tarek just talked about, to a database, and to a Redis cache. Now, so this is a really good architecture, actually. So many people use that. The problem here is that all those red boxes are single point of failures by themselves. I think that's kind of, usually you realize that. But additionally, every arrow is a single point of failure too. So you have 10 independent points of failure, and if you know something about probabilities, that means they almost add up. It's really bad. And that's all because network partitions are a thing. And many people are still live kind of in denial that they are so small, it's not going to happen to them. But everyone at some point will have a switch that's just dropping packets, or a network interface that's going to do weird stuff. And then they will start to believe. And arguably they are pretty rare, but every one of you who runs something at scale, like, I don't know, wargaming, rare events become common events because you just have so many of them. So what I'm trying to say is that you should think twice before adding new red boxes and new red arrows to your infrastructure. And with that in mind, let's come back to Tarek. Now, we know what microservices are, and we know what operational complexity is. And that kind of explains this. Now you know why premature splitting is the root of all evil. It's not just all the things he talked about. Additionally, you are incurring complexity on running all these things. It's a lot easier to have one database and one monolith. And once you go microservices, you get a highly distributed system. And are you equipped to do that? You may be like really frustrated by the downsides of a monolith on your day-to-day business. But microservices and distributed systems have many more exciting ways to wake you up at 4 a.m. because something doesn't work. So the question is, are you ready for that? So what I'm trying to stress here is that what you really want and what you really need are boundaries. You want to have boundaries and define them and adhere to them between your packages, your modules, and your classes. You do not need a physical network between your classes to have boundaries. And once you have boundaries established, the network part becomes so the upsides of microservices become much less important. But there are good reasons for having microservices. Tarek said a few ones. For me, it's mostly scaling out, because we still have the GIL in Python. And for interacting with that one Perl script that your boss wrote 20 years ago and nobody want to rewrite it. There are valid reasons. And once you have established boundaries, it's really easy to go microservices, actually, because the boundaries are already there. You just add a network. But all that is to say that complexity is reality. It's not the devil, but it's a price you pay. It's a currency. And the question here is, how does your budget look like? So how much complexity can you afford with your team, with the money you have? And the price can be actually quite high. So for example, Kubernetes is all the rage right now. And rightfully so, because it's pretty cool. However, running Kubernetes is super complex. Setting it up is really easy. So I've already set up a Kubernetes cluster by accident just by reading some blog post about it. That's not the problem. The problem is when it starts screeching, when you start having problems with that, and then you have to look into etcd, into Flannel, Prometheus, Docker. There are so many things that can break there. This is the complexity of running a cluster of that dimension. So if you can afford it, if you have people who can cope with that complexity, it's great, get it. But if you can't, you should maybe pay someone to run it for you, because that price is really high. And if you just take some tech that looks cool and it seems to work really cool, but do not understand it, do not master it, then Dante had some ideas about your future already many years ago. Now, speaking of stupidity, and this is of course on hyperbole, because most people are not stupid per se, but things seem often stupid in hindsight. And we act stupid, all of us. I act stupid. It could be because maybe we are sleep deprived because the baby cried all night. Maybe we are at a busy airport and we just try to deploy some important hotfix really fast before we board a plane. Or because you're hustling really hard to satisfy some well-meaning venture capitalist who has only the best intentions for you in their mind. So these things happen. And I'm going to defer to authority once more. In this case, it's John Alsport, the former CTO of Etsy, who he gave a lot of interesting talks and blog posts in his time there. And he does not believe in human error. And neither do I. I'm convinced that if a human causes an outage, it's usually because a system failed them. It's usually not malice or ignorance. It's usually a failure of a system. And you may remember the big S3 outage last year, where basically half of the internet went down. If you read the postmortem, which you should, because it's very interesting, it turns out that someone used a CLI tool with the wrong parameters. But the postmortem does not focus on what they did to the person, maybe fired them or cut their pay or demote them. No, the postmortem focused on a tool who failed that human, and that they are going to take steps to prevent this from happening again by improving that tool. So what I'm saying is that when building tools and APIs, you should always assume that the operator, for some reason, is drugged from the dentist, is consoling a crying baby, or is sitting in a boring conference talk waiting for it to become interesting. And if it takes just one click or one API call to lose all your data, someone will do that API call, someone will do that click. Maybe they will just try to clean their phone and will just accidentally tap on it. It will happen. And then it's your fault, because if you add sharp edges to your systems, to your tools, it's your fault if people cut themselves and bleed all over your company. So, and a part of that is also how you handle input. input into your systems, into your APIs, what's all these things. Because you have to really be careful about what you let in. And I fundamentally disagree with Postl's law here, because I think you should not be only conservative about what you send, you should also be very conservative about what you receive and let very little to interpretation. It should be very clear what data is valid and how you interpret it. This, by the way, was neither malicious nor a mistake. It was literally the only thing I liked about San Francisco. So, let's talk about data validation. And let's take something like invalid date strings. And I would say they are kind of like a time bomb, because they wander through your system, and the farther and deeper they get into your systems, the more damage they can do. Because the sooner you catch, the better you can respond to it. So imagine your web view catches an invalid date. Wonderful, it can tell the user your date is invalid. But if it goes right there to the ORM, it's just going to raise an integrity error and your user is getting a 500, which is not good. Other edges would be, for example, dunder init. You should never allow illegal or invalid instances of your objects even to exist. Just refuse to build them. Do not validate later. And I think validation is not enough at this point. I think your data should always be as soon as possible in a simple canonical form. So your business logic should not know about JSON. Your business logic should not use dictionaries at all. Because if you know the structure of some data, that's a class, that's not a dictionary. And a good rule of thumb is, if you never iterate over the keys of a dictionary, it should not be a dictionary, it should be a class. This protects you against typos, for example. Because Python will already warn you about wrong attribute names. If you use dictionaries, you have to wait for your key error to happen. Or even worse, if you're using get, and then this attribute never appears. That's not good. And this is called, there's a name for this actually, it's called primitive obsession, which is really a premature optimization. So try to have good abstractions and think about optimizing it later. Now, I could be talking about all this stuff forever. However, it's time for a plot twist. So we've said that complexity leads to normal accidents. Computers are complex, software is complex, and distributed systems are complex in the second. So what follows is that failure is inevitable. All those previous things I said, it's about minimizing risks, and it will help you, but eventually something will fail. So in practice, your reliability lands on a spectrum. On a spectrum somewhere from Twitter in 2007, which had a 98% uptime, which means they were down for 6 days. And say NASA in 1969, which landed on the moon, despite a human error on descent. But the computer in 1969 was smart enough to compensate for that human error in using it. The problem with NASA-style reliability is that you need a genius writing your software who also will just invent the whole thing about software engineering while writing that software. So you may have to scale down your expectations unless you have Miss Hamilton on your staff, in which case I would like to apply for an internship. So, failure is inevitable. What do you do? Well, there's only 3 things you can do. You can minimize risks, which I talked about before. You can prepare for failure. And you can deal with it. That's your reality. And a great example of how to do this well was last year, when an A380 from Air France, of course, lost an engine over the Atlantic. And this should not happen. I think we can agree on that. It's kind of weird. Like, planes should not lose their engines over the Atlantic. But Airbus engineers expected this to happen. And because they expected this to happen, 500 people get to live today, which is kind of cool, I think. So this is basically how your systems should behave. Anything can happen, and the question is how you cope with that. Even though, hopefully, people are not in a risk of dying. So, how do you expect failure? You usually have to do it actively. So that means that you need systems in place. So if you have a system that is supposed to do something, you have to actively check and monitor that it's actually doing what it's supposed to be doing, because otherwise nobody knows, right? And you have to check for outages, you need to instrument your system so you can detect anomalies, and you need good error reporting. Because silent failures are the worst failures. Because you think everything is fine and your users cannot use your web page. That's pretty bad. And I've talked about these things in the past 2 years. My taste did not change. I still love Prometheus, which is great for instrumenting your system, instrumenting your software. It's great for monitoring all of the above based on those metrics, and for alerting based on those metrics. And I also like Sentry, because it's open source, it's a Python shop, and yeah, David Kramer may or may not have a video of me singing Beyoncé in a karaoke bar in Bilbao. So, in your code, how do you expect a failure? Well, you catch exceptions, right? And that's the easy part. You just, even if it happens, you know how to handle it, and it's very obvious and it's very fast. So the problem is with remote systems, because instant failure is actually a good thing. It's a rare thing. So like when you get a connection refused or a HTTP 500, that's easy to deal with. The much worse scenario is that nothing happens for minutes. So whenever you do something remotely, you have to put a timeout on it. And one missing timeout in a database driver was enough to ground an entire airline in the United States. So people get this wrong all the time, and it's still one of the most important tenets of distributed systems. If you don't have timeouts, your system will at some point just hang, and you will not know why. Now, what happens? What should you do if you have a timeout? Do you just carry on? Because it's kind of bad for both your user, because your user is getting very long, very useless requests or responses. So if your timeout is 1 minute, and when your user clicks some link, it takes 1 minute until they get a 500, which is not good. And also, imagine your system is being overloaded. It just gets all these useless requests, which are straining the system. It's also not good. So for this, the circuit breaker pattern is really, really good. Sadly, I don't have enough time to explain it to you in its full, but it helps you to isolate failing systems until they are okay again. And I'm going to refer you to the talk page to read more about that. So, I've said before that adding more components to a system is bad. But if it's the same component, and if you put something that is much more reliable than your software, like HA proxy, it might actually become good again. And I don't say this lightly, but HA proxy is really good software. It's so in that case, you are not reliant on one service working properly, but you should have at least 3 actually. Because in the military they say 2 is 1 and 1 is none. So you never want to arrive at the point that you have only 1 service or no service left. So you should start with 3 for the really critical systems. And this made the internet almost unbreakable unless everyone is using the same DNS provider or the same storage service in the same region, like we had before. Now, this works at every level, like the network level. You should have more than 1 switch and more than 1 uplink to the internet. On server hardware, you should have more than 1 server, obviously. At data centers, ideally, that's not that simple, but if you're big enough, you should have some redundancy there too. And of course, it works with backups. Because if this is all it takes for you to lose all your data, including your backups, you do not have backups. You just pretend to have some. Also, if you do not test your backups, if you do not restore them from time to time, you also do not have backups. You can ask GitLab about that. So, being dispensable means also that you must not become a knowledge silo. So when people ask you something, write it down. If there's a regular task, something that cannot be automated, but it's a standard procedure, write it down. And finally, if there's something that needs to be done in a case of emergency, write it down. Because thinking that you remember all those things while your server is burning or your app is down and your customers are yelling at you is a very dangerous fallacy. And the whole staple of aviation security is that there's a checklist for everything. So even if some passenger had too much fiber for their breakfast and the toilet is clogged, the pilots will take out a checklist. That's how it works, and that's why not a single plane crashed last year. As I've heard, this year is not that good already, but yeah. So having contingency plans is priceless. And it doesn't have to be steps to do something to recover service. It also can be communication. So you should tell the social media team that your servers are having problems so they don't lie to your customers and tell your customers to restart their computers because everything is fine. Now, how do you deal with failure in your app? What do you do when your database is gone, when a web service returns invalid data back, or you're getting timeouts? So first is don't make it worse. Failure containment should be your #1 priority. Because in the worst case, you get a bunch of cascading failures, and your whole system, your whole data center just melts. Because some very unrelated systems have had problems. That happened even to GitHub at some point. So this is very hard to get right, but it should be #1 priority. Now, let's talk about something very simple that has a very big impact, retries. In distributed systems, retries are essential because we always have transient failures. Things happen, things break. But they're also super dangerous because if you use them loosely, if you just do a for loop trying to retry something, you're gonna DOS yourself. Or in a case of a third party, you also DOS them and also maybe get cut off, you get on a blacklist or something, and then you have a very uncomfortable conversation with the other third party about why you do not act properly. Now, what you need to do is to back off. But how long? Did you just run into some deployment thing and the application just wasn't ready yet? 1 second and everything is fine. Maybe a service is overloaded and you need to provision under a server. 1 minute should be fine. But maybe some hardware is broken and someone has to go to the data center and replace a switch. Well, then you go for maybe 5 minutes to just check back if it's back on again. So the answer is you do all of that. You just start with a very short period and you rise that period exponentially. But if all services do that the same way, you still have a lot of load in the same moment because they all do their retry at the same moment. So for that reason, you have to add a jitter, which is just a random number you add to that number that you just computed. And they will space out the retries slightly, maybe like by seconds, but it's usually good enough to take the brute force of all of your systems retrying at once. And while this is kind of intuitive, there's still some problems with it. Because let's assume you have a policy of 3 retries per request. Now, let's assume the backend is your responsibility. And Tarek really inspired you with microservices, so you add some more services. Now, you have 3 times 3, which is 9 retries. But this is not even close to microservices, so let's add 1 more layer. And you're DOSing yourself again. So what this is called is a combinatorial retry explosion. And you are hitting C with 27 retries just because a user clicked 1 link. And now imagine if C was flaky because it was overloaded. Now it's toast. So the simple solution is to have retries only on the top. So it's only 3 retries and no one else. But you don't always know where your top is. And maybe you have some systems that talk directly to internal backend B. How do you do that? Well, then it gets complicated. Then you need things like retry quotas and stuff like that. And this is complexity through microservices, which you just did not have before. Now, there's more to be said. Things like back pressure, which you should have. Unbounded queues, which you should not have. It's mathematically proven that unbounded queues are worse than no queues. Just don't have them. Again, I don't have enough time. There will be a link. Check it out. Now, the next one is having failures and not knowing why things fail or how they fail is kind of terrible. You want to know what happened and why. So if you do something like this, especially in public libraries, I have a lot of opinions. Because how am I supposed to debug this? This is basically impossible unless I PDB through it, which is kind of hard in production. Also, what I like to call vanity exceptions is something like this, which is not better at all. You have still the same problem. There are no error details for me available. So what you want to do if you want to have your own exception, is called exception chaining. So this is Python 3, and it will just attach the original exception to your exception. So you have insight about what went wrong. If you are still on Python 2, there is some hope, because 6, the library, has a raise from function, so you can use the same principle. But usually, if you're writing a library for other people to use, I would advise to just let it fly. If you don't know how to deal with an exception, let it be. I'm probably more capable to do something sensible with it than you in the library. The next one is kind of counterintuitive. If your app is unfit for work, just don't try too hard. And it's like, if your pool is broken, what do? You could add complexity, try to reconnect, and serve errors. Or you just do this. This is called crash-only software. And it's not something I've invented. There's scientific papers about that. And it will also call your add-exit handlers to clean up the mess behind you. And more often than not, this is better. This is easier. So I'm running out of time, so I'm going to talk really fast now. I'm sorry. So what I want you to do is to fail fast and fail loudly. A crash is always better than a hang. I think you can sympathize with that as a user. If I click on a link, immediate error is better than waiting a minute for an error. Depending on your audience, a stack trace might be even better. But of course, you have to be careful about exposing secrets. So Redis, the key value store, takes it even further. When they crash, they give you not only a stack trace, but they run a quick memory test, because most Redis crashes are caused by faulty memory. So once you've done that, you need to focus on recovery. And that means that the MTTR, which is the mean time to recovery, reigns supreme, basically. So, because if you accept that the failures happen, and even write your software crash only, it becomes much less important whether your service goes down, and it becomes much more important that it comes up again really fast. And for that, you have to make sure that no humans are allowed with restoring your service. Because if you have a power outage in your DC, which still happens, it shouldn't happen, but it can happen, how are you going to handhold all your services to come up again? That's probably going to take an hour until everything is up and running. So what it means is that your application must not have any expectation whatsoever what is present when you start. So when I take a Docker container from your production on my notebook, it should do something meaningful. It should try to connect to the services, but if it doesn't work, it should try again. Or just crash. And then in that case, you have to handle this behavior outside of your application. I personally usually just have a for loop with a back off, and it works fine. Eventually, it will come up, and your service is restored. One more slide. So what is the secret to a long, undisturbed vacation? Apparently, $9 Mai Tai in plastic cups, but also build fault-tolerant systems that recover fast and autonomously, and throw your phone into the sea. So this is the promised link. The QR code will get you there too. Follow me on Twitter, and don't be shy. Talk to me about all things DevOps and software engineering. I did not come here for the weather. Thank you very much.
Thank you. So I believe that our application will become more reliable after this presentation, but we have time for 2 questions. So if you have any, please ask.
Thank you for the presentation. You mentioned in the list of the important to-dos to have docs. But
come again, please. Could you talk more into the?
Yeah. So is it better now?
Yes.
Okay. So I wanted to ask about docs. Do you see a way to automate somehow the docs part of the to-do list? Because what is not automated is prone to human error.
Yes.
Which doesn't exist, we figured out, but nevertheless. So is there a way to make it better?
I don't think there's something like a general solution to that, unfortunately. So, I mean, there are things like you should be careful to not have recovery docs on a wiki which runs on your own servers. So if your data center is down, you cannot access them. But no, I'm afraid there is nothing really automated. No, it's a human thing. It's mushy. Because if you could like add a lot of automation to it, you probably could automate the problem itself too, I think. I don't know. It's usually the last scraps of things that just can't be automated, and they're usually very diverse. You know, it's like press that button or call this number. So those things usually do not have a lot of common, except that they cannot be automated.
Okay, thank you.
At least I have not found anything.
One more question? No? Okay, thank you.